Cosmologists looking for the center of the universe have settled on the Big Bang theory and have been often frustrated by an endless barrage of correction factors which tend to increase in both the amount of parameters and their magnitudes as the data accumulates. Mouthful, but we all know what it is if you've been following any science news. The luminocentric principle gives us a different coordinate system to work with. No kidding. Okay, so let's look at the electromagnetic spectrum. In particular, let's look at microwaves. They are about a meter in length. So if you remember how television antennas were shaped on top of the TV before the World Wide Web and before we got all our media from the internet, they were shaped, they had like about, maybe 10 centimeters in length, maybe more. So there were gray dots on the screen everywhere if you weren't on a channel. And those gray dots were the microwave cosmic background. But the idea here is that the antenna on that TV was it was never stationary with respect to vacuum. In fact, it was always, we are traveling very fast with respect to vacuum. Okay, I think at the speed of light, at what we think of as the speed of light, but I'm not prepared to go there yet. You see, the fact is that we know we are traveling very fast with respect to vacuum. There's all sorts of motions that we can add. So that antenna was happening on the cosmic microwave background, which is stationary. Now, if the cosmic microwave background didn't move, what it did is it stretched. So what we're guessing here is that these they stretched all the way down from gamma rays. And if for some science, if for some other reasons in science, we can find out that they were indeed gamma rays in the beginning, then we know, and we know what we mean by this beginning, like we mean 15 billion years ago, then we can calculate how these objects lose energy and gain length with time. The luminocentric principle gives us blah. Instead, we view the expansion of electromagnetic waves as a loss of energy over time, and that loss in energy has been traded by a gain in length, meaning the length between the North and the South Pole, or area, meaning the area of the circle as it's rotating. We have the advantage of dealing with a stationary electromagnetic wave, that is to say, a magnet rotating about a center point that is itself fixed with respect to vacuum. Yes, the fulcrum of the wave, so to speak. Knowing the center of rotation will not be displaced in space. Indeed. You see, this is how we this is how we just got ourselves a coordinate system. Because those points will not be displaced in space. And now I go into how the Doppler effect is really, because we are moving in space, what we are measuring with Doppler effect for light, if there is one, is that we are examining our displacement with respect to what the star's trajectory was a long time ago. And I'm not saying with respect to because you see the star It didn't emit the photons out into space. No, the star went flying out into space and it left behind the stationary photons as a trajectory that it made. And we are doing, our star is doing the same thing, but with a different trajectory. So what we're really measuring in with it, with what we're really measuring with the Doppler effect for light, if there is one, is the relative speed of two trajectories, if you will. It's really our speed, right? Because the trajectory is a stationary object. Those photons left behind by the star is a stationary marker of the star's trajectory. And we're not stationary with respect to that trajectory. So we're measuring that. Thank you.